All right, how's everybody doing? Welcome back to the Math for 140, Math for Healthcare video lecture series. So, today we're going to start with some introduction to probability. Hopefully, we got some good practice with sets and Venn diagrams. They will be very useful through this whole probability. So, that's the rest of the course, really. Think about that as, and maybe to motivate before we get into some vocabulary and then the formulas, is let's just think about why sets would come up and what the probability have to do with it. So let's see. Let's suppose, first of all, let's just suppose I got a spinner circle. I'm not going to be able to draw it perfectly, but basically broken into three even pie-like pieces. And we're going to, let's see here. We've put a little, there's going to be a spinner on here, an arrow. It's supposed to be in the center, you know what I mean? And we're going to spin that. And we want to see which color it lands on, where we have a blue piece. We have a green piece of the pie. And we have a red piece of the pie. All right? Simple. So we're going to spin that. What is the what do we think? What is the probability of spinning, or really spinning and landing on green? Okay. Well, I want you to think about that for a minute. Hopefully we came up with that probability is 1/3. Okay. Now what does this have to do with sets first? Well, I think that the way most of us would do that is, well, what are we counting? The possibilities, which is, so we're counting the size of the set of all possibilities, which is, let's say, blue, red, green. Okay, that's the, we're going to see later, that's called the sample space, but that's all the possible spins, right? They're all equally likely because they're the same size. Okay. And what are we interested in? We're interested in the set when it's coming up green. That in this case just means that. And notice that the size of this set is 1, which is my numerator over here. And the size of this set is 3, which is my denominator here. And that's exactly how we're going to find probabilities. So sets become quite an important part of your probabilities and being able to define those sets and understand what you're working with, including also unions and intersections of sets. But we'll see that as we move forward. I want to think about here for a minute is, well, what does the probability of landing on green mean to be 1/3? What does that mean? I want you to think about it for a minute. I will stop you if you think that means that there's a 33.3% chance. I'm really asking, what does that mean? Okay. Well, what it doesn't mean is that we're going to land on green 1 out of every 3 times. No, right? I think we all know that. So, what do we mean is really in the long run, if we spun this, say, 1 million times, we'd expect to land on green about a third of those spins. Third of the, so whatever, 333. Sorry. A third of the 1 million, right? Now, that's important. We're gonna learn how to find probabilities, but understanding what they actually mean is important. They're not deterministic. They happen long run averages, basically. Right? They're not deterministic. It doesn't happen exactly one out of every 3 times. You can't depend on probabilities that way. And hopefully, we're going to learn how to use that to our advantage, and at least not let it cause a disadvantage. All right, so some vocabulary first. Sorry, it's a little crooked. We're going to deal with it though. In discussing experiments, we'll use the following terms. A sample point is an outcome of an experiment. A sample space is the set containing or consisting of all possible sample points of an experiment. For instance, in our last example, the sample space was the set B for blue, G for green, and R for red. That was all the possible sets. And an event is a subset of a sample space of an experiment. And certainly, right, would we say, I can't remember what we did, but let's say it was blue getting a blue. Well, that's certainly a subset of this sample space. Okay. And that's important. It has to be a subset. You can't, if it's not in that sample space, it's not possible to do. Now, an event is said to occur in a trial of an experiment if B contains the observed outcome. Okay, for instance, ours was blue. Another way to think about that is another event when we had the sample space, say, of blue, green, and yellow. I could ask, well, what about the probability of getting blue or green? Well, that looks like this, right? And that event, let's call that set E, and it is still a subset of our sample space. That E, it has occurred. It's occurred that we've gotten a blue or a green if one of those things happen. Okay. Question. 6-sided die was rolled and a value of 1 was observed. Which of the following events did not occur? Take a minute to think about that. A number greater than 1 was rolled. That did not occur. 1 is not. Let's see. The other ones, let's see. 1, 4, 5. That's obviously 1 is an element in there. All right. Or the set containing 1 is a subset of it. Similarly with this S, which is the sample space, odd number. Well, what's that set? That's going to be 1, 3, 5, right? A number greater than 1 was rolled. This here, 1's not in there. A number less than 3 was rolled. 1 would be in that set as well. Sometimes an event is described in English instead of written as a set. It is up to us to determine which subset of the sample space corresponds to the description. And this happens a lot. All right, this is part of looking at solving problems. Fair die rolled, and the number that falls uppermost is observed. The sample space, well, it's going to be the integers 1 to 6, right? That's our sample space. Notice we're doing sample spaces where each one of those things are equally likely. That's going to be very important in the beginning of our probability. An odd number was rolled. Oh, what's that? Oh, yeah, E equal to 135, just like we saw in the last slide. A number less than 4 was less than, so this is an event F, the set containing 1, 2, and 3, because 4 is not less than 4, it's less. And we always got to be careful what they ask for, less than or equal to. Okay. A prime number was rolled. 2, 3, 5 are the only prime numbers between 1 and 6 inclusive. And we note that 1 is not considered a prime number. You will not be tested on that. I just want to let you know. Some people are mistaken there. All right, so since events are subsets of the sample space, we could always use set operations on events. In other words, okay, let's E union F. We know what that looks like here. What does it mean? That either the event E or the event F happened, right? Intersection, the event E and the event F happened. And E complement is E did not happen in words. Now, let's look at an example. Fair die is rolled and the number that falls uppermost is observed. That just means roll a die and read them like you normally would. The sample space is S equal to 1, 2, 3, 4, 5, 6. We'll let E be the event that an even number is rolled and F be the event that 1, 3, or 4 is rolled. What is E union F? Well, that's the event. Well, we get a 1, a 2, a 3, a 4, or a 6. It's just missing the 5. That's the only one that's not there, right? That's E union F. I don't have to write it in order. I did it just to see it that way, but it's not necessary. Sets are unordered. So it's rolling any number. What is E intersects F? That's saying E and F has to happen. It looks to me like it's only the singleton 4. E intersect F is the same as saying rolling a 4. What's E complement intersect F? Okay, that's going to be rolling an odd number and 1, 3, or 4, so that's going to be a 1 or a 3. Rolling a 1 or a 3. Don't mistake in this or with, remember, intersection is and. This is saying E complement and F are happening. E complement intersect F complement, and that is just rolling a 5. Now, suppose we have an experiment where events E and F. We call E and F mutually exclusive if and only if their intersection is empty, meaning they cannot happen at the same time, right? All right, and here's a picture of mutually exclusive events. Let's see here, we're rolling a fair die again. Are the events of rolling an even number and rolling an odd number mutually exclusive? Yes, they are, right? They cannot happen at the same time. Another way we could check that is rolling an even number, intersect, rolling an odd number. That is the empty set. Consider the experiment where a 10-sided die is rolled and the number that falls uppermost is observed. Which of the following pairs of events are mutually exclusive events? Okay, so let's see here. What we got? The roll is less than 5 and the roll, 10-sided dice. So we're playing Dungeons and Dragons or something here. The roll is less than 5 and the roll is even. Are those mutually exclusive? let you think about that. 1, 3, 4, 5, 6. The set containing 1, 3, 4, 5, 6. And the roll is greater than 5. Are those mutually exclusive? The roll is even, and the roll is a prime number. Are those mutually exclusive? The roll is even, and the roll is 9. So D, the roll is even, and the roll is 9 is mutually exclusive. Let's see, why aren't the rest? The roll is less than 5, and the roll is even. Well, 2 is both less than 5 and even. 1, 3, the roll is greater than 5. There, 6 is in the intersection. C, the roll is even and the roll is a prime number. 2 is going to be in the intersection. All right. Mutually exclusive. An experiment consists of tossing a coin 3 times and observing the resulting sequence of heads and tails. Determine the sample space of this experiment. Here we're going to use a tree diagram. Go ahead and hit pause for a second there and take a look at that. Basically, we want to follow all the possibilities. First toss could be heads or tails. Second toss, heads or tails. Right? And what's going to happen here is we follow every path to the end, and that gives us our equally likely sample points. Right? So, what is our sample space? So we write all those down. All 3 heads. 2 heads first. Notice we do it in order. We don't just say 2 heads. We think about the first, second, and third coin. This is to keep the sample space of equally likely events. All right. Notice that the size of S is 8. For B, by scanning the sample space S, determine the event E that exactly 2 heads appear. We just look through our sample space, and we pick out the ones with exactly 2 heads. And it looks like we got 3 of them that are sitting right there in E. Now, at least 1 head appears. Well, that's everything but the all tails, and so we should have 7 that appear in this set F, or event F. Now, here's our formula from earlier. Basic probability principle that we did just off the cuff. I guess we didn't show the formula, but if S is a sample space of equally likely outcomes, this is important, this equally likely, then we could just count things. And E be a subset of S, the probability that event E occurs is the number of elements in E divided by the number of elements in the sample space. So almost every probability problem you could start with finding what's the size of the sample space. That's an important thing. Notice we're really mainly curious about the size. Now for any event E, since E is a subset, the probability of E has to be greater than or equal to 0, because the size of E is greater than or equal to 0, and the size of S is greater than or equal to 0. And it's less than or equal to 1, because why is this? The size of E is less than or equal to the size of S, because it's a subset. That's right, since E is a subset of S. So it's going to be true for all events, because all events are subsets of the sample space. All right. We'll cut it off there and continue on. We'll come back and start with this formula and then start practicing finding probabilities. Okay. Have a great day, and please let me know if you have questions.